All right, so this week's topic is geometric sequences and series. And so I've got the definition up here. So geometric sequence is a sequence where each term is multiplied by a constant r, called the common ratio, to get the next term. Or you can think of it as a sequence where the ratio of any term to the previous term is always constant. So why these two different definitions? They're really saying the same thing. If we just look at a simple example, a classic one, 2, 4, 8, 16, 32. Dun, dun, dun. So that is a geometric sequence, and we can see that we're multiplying by 2 each time to get the next term. So as long as you're multiplying by something each time to get the next term, it's geometric. Remember, adding is arithmetic, multiplying is geometric. So we can see that we are just multiplying by 2, 4 times 2, 8 times 2, 16 times 2. But another way you can think of it is if you take the ratio of any two consecutive terms, it always has to be the second divided by the first. So for instance, let me get rid of this. So let's say that I wanted to look at these two consecutive terms. 32 divided by 16 is 2. So it always has to be the second divided by the first. I could look at these two consecutive terms and say 8 divided by 4 is 2. And so every time I divide two consecutive terms, I'm always going to get 2. Therefore, it's geometric, and that constant ratio, the common ratio, is 2. Okay, so now let's look at deriving the formula for a sub n. The explicit formula, the formula for the nth term, whatever you want to call it. Let's look at this one, almost as easy as the one above. Let's just say that we start with 3, and then the next term is 6, and then the next term is 12. If this is geometric, can you already predict what the next term is? And if you were thinking 24, you are correct. Because 3 times 2 is 6, 6 times 2 is 24. We're just multiplying by 2 each time. Okay, so I'm going to make a table like we did before. We have the first term, which is 3. We have the second term, which is 6. We have the third term, which is 12. We have the fourth term, which is 24. And we have the fifth term, which is 48. But now let's look at rewriting these using the method that we're actually using to derive the next term. So I start with 3, and then to get 6, we multiplied 3 times 2. And then to get 12, we took what was above, but we multiplied by another 2. To get the 24, we took the previous term, but we multiplied by another 2. To get the next term, we took the previous term and multiplied by another 2. And we just keep multiplying by another 2. And we know that when you multiply over and over again, repeated multiplication can be rewritten exponentially. So this is, 3 times 2 to the first power. 12 is 3 times 2 to the second power. 24 is 3 times 2 to the third power, and 48 is 3 times 2 to the fourth power. And if you take a look, the power that we're using with the base is always 1 less than the term number. The second term, we only multiplied by 1 2. The third term, we multiplied by 2 of them. The fourth term, we multiplied by 3 2s. The fifth term, we multiplied by 4. So if we go ahead and generalize for the nth term, we're going to take 3 and multiply by 2 n minus 1 times, where 3 was the first term and 2 is the common ratio. And that's what's going to give us our formula for the nth term. So for a geometric sequence, the nth term, don't know what I was doing there. The nth term is a sub n equals the first term times the common ratio to the power of n minus 1. There we go. So I'm going to go through all of the stuff, but then we'll look at some examples of these. I'll put the examples at the end. So now let's look at partial sums. So partial sums, oops. Actually, I'm going to go to a new page for this. So to derive the formula for partial sums, it gets a little more complicated than what we did for arithmetic, but it's very similar. So this is going to be the derivation of the formula for the nth partial sum S of n of a geometric series. So now we're talking series. We're going to start adding them up. Okay, so I'm going to go ahead and write a formula for S sub n that we do know. It's not going to be very helpful in finding an actual sum, but S sub n is by definition the first term plus the second term plus the third term plus the fourth term all the way up till the nth term. But rather than writing it as a sub 1 plus a sub 2 plus a sub 3 all the way up to a sub n, I'm going to rewrite it like this. The nth partial sum, the sum of the first n terms is the first term plus the second term, which can be written like that, plus the third term, which is a sub 1 times r squared, plus the fourth term, and so on until we get to the end. And remember, the end, we only multiply by r n minus 1 times. So the nth term, you only have to multiply by r n minus 1 times. So that's, I guess we have a formula there, but it's not a very useful formula. So what I'm going to do is I'm going to take that same formula, but I'm going to multiply both sides by r. So I'm going to multiply this side by r, and I'm going to multiply the entire left-hand side by r. But I'm going to write it in a convenient way. So this term, the r would actually distribute to all of these terms. So if I multiply this term by r, that's going to become a sub 1 times r. And if I multiply this term times r, it's going to be a sub 1 times r squared. If I multiply this term, the third term, by r, it's going to be a sub 1 times r cubed. And if I multiply this term, it's going to be a sub 1 times r to the fourth. And I keep going, and I multiply the last term by an r. That means I'm actually multiplying by n r's. So I have all of this. So by doing it, by writing it this way, it looks like I have the same thing as above, but I just lost this. But really what I did, every single term got multiplied by r. And then I'm just lining up my like terms. So what I'm going to do is I'm going to subtract the equations. So on the left-hand side, we're going to have s sub n minus r s sub n. But on the right-hand side, some stuff cancels. This is going to cancel, this is going to cancel, this is going to cancel. We'll have this term, it'll cancel out with something above it. This term is going to cancel out with something below it. But we're going to have this guy off at the end that won't cancel. So this term and this term don't cancel. So I do have a sub 1 minus a sub 1 r to the n left. And now I actually have a formula that's going to be useful. I can go ahead and take this formula and solve for s sub n. I'm going to factor that out, and I'll have 1 minus r. I'm also going to, you don't have to factor out the a sub 1, but when you see the formula written in most books, and I think it's just because it is easier to work with, we usually factor out the a sub 1. So I'm going to factor that out too. And so finally, if I divide, this is the formula for the nth partial sum. So the nth partial sum is the first term times 1 minus r to the nth over 1 minus r. I am going to go ahead and kind of summarize this here. So the nth partial sum of a geometric series is S sub n equals a sub 1 times 1 minus r to the nth over 1 minus r. But very important, a sub 1 is the first term and n is the number of terms. If you're doing this after watching and doing the homework for arithmetic series and sequences, you know that that's important, understanding what these are. A sub 1, when you're doing these formulas, it's especially if it's written as a summation, as a sigma, a sub 1, the first term isn't always plugging in a 1 for n. And then you have to be careful of how many terms you're going to go. So, well, like I said, we'll do an example. You'll see what I mean with that. But just be careful about what the parts of the formula mean. Now, there's one other idea, and then we're going to get to examples. So it's going to be nice short video week for you guys. The last example is, what about infinite sums? Because believe it or not, we can actually talk about infinite sums with geometric series. Let's look at that a little bit. Finding an infinite, sum of a geometric series. So what are we talking about, first of all? An infinite sum means you're just going to keep adding and adding and adding and adding, and you're never going to stop adding. You add an infinite number of terms together. So, for instance, if I had the summation as n goes from 1 to infinity, so we actually put the infinity in the top, so our upper limit's infinity, we're never going to stop, of, let's just look at this one, 3 times 2 to the n. We'll say n minus 1. So it'll be the same one we did before. Well, that means it's going to be 3, and then we're just going to keep multiplying by 2 each time. Plus 6, plus 12, plus 24, plus 48, plus and we don't stop. Well, of course, we're going to get infinity. Now, we don't actually say equals infinity because infinity actually is not a number, so you can't be equal to infinity. But we put this arrow and said it tends to, it approaches positive infinity. This sum is just going to keep getting larger and larger and larger. Well, that's not very exciting then. Wouldn't all infinite geometric series do that then? You just keep adding forever and ever and ever, and wouldn't it always just keep getting bigger without bounds? And this is the crazy thing, because the answer is no. Think about this one. So, as n goes from 1 to infinity, of 1/2 to the power of n. So let's look at this. Okay, so when n is 1, 1/2 to the power of 1 is 1/2. When n is 2, 1/2 squared is 1/4. When n is 3, 1/2 cubed is 1/8. And I think you see the pattern here. It's just going to be this series. And believe it or not, this series does not get bigger and bigger and bigger without bounds. It's actually bounded by something. This is a nice one you can see visually. Imagine a square. And I'm going to represent this sum, since they're all fractions, I'm just going to keep shading in fractions of the square. So first I'm going to take 1/2 of the square and shade it. Okay, so there's 1/2. But now I'm going to add 1/4. So I've just added 1/2. Now I'm going to add 1/4, which would be that piece right up here. Now I'm going to add 1/8. And 1/8 is just half of a fourth, so I'm just going to cut this other fourth in half. And I have that. And then 1/16 is just half of an eighth, so I'm going to take this white eighth that's left over, cut it in half. And I just keep doing it. I take half of what's left and shade it. So I take half of this white part and shade it. I take half of what's left and shade it. I take half of what's left and shade it. I take half of what's left and shade it. Now eventually it's going to get so small that my pen is too big to be able to do this, but you can see that if I can zoom in on this part, I'm always going to take half of what's left and shade it, but that means there's always going to be half that's left unshaded, which then I can cut in half and shade half of it, but then there's half that's left unshaded. There's always going to be something left unshaded, but I'm never going to shade more than this one square. I'm getting closer and closer and closer to shading the whole entire square in. Never going to quite get there, but I'm going to get closer and closer and closer to it. Now, this is where it's weird. Because up here, remember I said we can't equal infinity. Infinity is not an actual number. But these numbers, if I could add for an infinite amount of time, if I could add an infinite number of terms in this series, not only does this series approach 1, it actually equals 1. The second I cut it off, the second I stop, now it's not equaling 1 anymore. It's really, really close to 1, but it's not going to be equal to 1. I have to go forever. These 3 dots here are really important. I have to be going forever. I have to be adding an infinite number of terms in order to say this equals 1. But I can say it equals 1. It's a weird idea. It gets into something called limits, which you guys are going to study next year in calculus. But yeah, it's kind of crazy. So sometimes geometric series tend towards infinity, but sometimes geometric series actually have a sum, or I should say infinite geometric series. Sometimes infinite geometric series tends towards infinity. Sometimes infinite geometric series have a sum. They're bounded by a number. They're never going to get bigger than that number, so we say it equals that number. So how do we find that number? Well, let's take a look first of all at these numbers right here, and then these terms right here. So think about what was it about the second series that made this one bounded by a number, that didn't make this thing explode up to infinity. Meanwhile, this one up here, the top series, did go towards infinity. So think about what the difference was between these two. Why does the bottom one have a sum but the top one doesn't? And if you want to pause the video to think about that, that'd be great. Okay, so if you pause the video, or if you already figured it out, it's because these numbers here got smaller and smaller and smaller. And they got so small, if I kept going with this, just a few more times, these numbers are going to get so small, they're getting really close to 0. These terms just keep getting larger and larger. These terms getting smaller and smaller and smaller and tending towards 0. 1/2, not that close to 0. 1/4 is a little closer to 0. 1/8 is even closer. 1/16, even closer to 0. 1/32, even closer to the 0, and so on. Each term is going to get closer to 0. So as long as the terms get closer to 0, you're going to get a sum. So how do we know that that's going to happen? Now let's take a look at this. Think about these two given series in summation form. How can you just look at these and know that each term in the second one are going to get smaller and smaller and closer to 0, whereas on the top one, each term will just get larger and larger and larger? So think about that one. And if you were thinking it had to do with this base, you are correct. when the base, and actually we're going to, it's important to look at the absolute value of the base. I could have had negatives in here, but if the absolute value of the base is greater than 1, that's what's going to make the magnitude of each term get larger and larger and larger. Whereas if the absolute value of the base is less than 1, then the terms are going to get smaller and smaller and smaller and close to 0. And if the base actually equals 1, think about that. What would happen if the base was actually equal to 1? Do you think we'd go towards infinity? Or do you think we get a sum? And if you were thinking we're going to go towards infinity, you would be correct. Think about this guy right here. If n equals 1 to infinity of 5 times 1 to the n minus 1. If n is 1, we're going to have 1 minus 1, which is 0. Anything to the 0th power is 1, and 5 times 1 is 5. When n is 2, then we're going to have 1 to the 1st power, which is still 1, times 5. We're still going to get 5. If n is 3, we're going to have 1 squared, which is still 1, times 5, which is 5. We're just going to have a whole bunch of 5s. These terms are not approaching 0. If they are not approaching 0, you will tend towards infinity. So, let's go ahead and try to summarize this and see if we can go ahead and find a formula. Now I'm going to go ahead and put this formula here. The nth partial sum of a geometric, oh my goodness, I can't spell, of a geometric series. We just looked at that earlier. That was S sub n equals a sub 1 times 1 minus r to the nth over 1 minus r. But now let's see if we can get the infinite geometric sum. Well, take a look at this formula here. The key is going to be this part right here. If the absolute value of r is less than 1, then when you start raising r to the nth power, when you go towards infinity, that's going to get smaller and smaller and smaller, and this is basically going to become 0. And then you're going to have 1 minus 0, which is just 1. It makes your numerator just a sub 1. But we can't simplify the bottom at all. But luckily the bottom's already pretty simple. And so that's basically our sum right there. If the absolute value of r is greater than or equal to 1, the sum does not exist. You can say the sum does not exist. Sometimes you'll hear the term diverge. The series diverges. Diverges just means it doesn't tend towards a sum. It's not bounded by a number. It diverges. It doesn't converge to a number, so it diverges. So that's essentially the notes. Now we're just going to do some examples. All right, so the first example. Example 1, find a formula for the nth term. And I'm going to do 2 in these. Let's say that a sub 1 is 12, r is 1/7, and we want to find the 10th term. All right, this one's not so bad. Remember, we have a formula. The formula for the nth term is a sub n equals a sub 1 times r to the n minus 1. You just plug in. We're given everything we need. We know a sub 1. We know r. So the general rule for a sub n for the nth term is the first term times r. Whoop. Get the right r. To the power of n minus 1. And there we go. There's our formula. And then if we plug in this case, we want the 10th term. And actually, I should make that say a sub 10. So the 10th term is going to be 12 times 1/7 to the 10th minus 1. And if we work that out, we're going to have this. Now, these numbers do get crazy. Exponential growth, you know, it just grows really fast. So if you work this out on the calculator, for instance, I'm getting 2.973 times 10 to the negative 7th. So I'm getting a really small number. Remember that? Whoops. That would be 0.12345672973. You have to take this decimal point and move it over 7 places. So it's a really, really tiny number. So sometimes your answers for your homework, you're just going to get approximations because your calculator's not going to be able to show you the exact number. It's okay. Don't worry about that. So there's the first one. Pretty straightforward. Let's look at one that's not quite as straightforward. So what if I told you that a sub 11 is negative 3072 and a sub 17 is negative 196,608. What? Huh. We want to find a formula for a sub n. Remember, we're using this formula right here. Here, I'm going to move this up. So how are we going to find a sub 1 and r given this stuff? And you can, just like, again, if you've gone through the video that I did with arithmetic, there's a conceptual way to think about this. The conceptual way and the algebraic way, you still do the exact same arithmetic. It's just two different ways of thinking about it. But just like we did arithmetic, we're going to make a system of equations. Now, when you're making your system of equations here, I find it always easiest if you put the bigger term number over the smaller term number. It doesn't matter that this number, the 196,000, actually it's smaller in this case because we're talking negatives, but it has nothing to do about this number versus this one. Not the term value, the term number. 17 is bigger than 11. So I'm going to set these up. I'm going to plug 17 in for n and this number in for a sub n and make one equation. And I'm going to do the same kind of thing for this. So my first equation for a sub n, I'm going to put negative 196,608 equals a sub 1 times r to the, and it's the 17th term, and 17 minus 1 is 16. So I can't fill in for a sub 1 or r because I don't know those yet. So there's this equation from this term, and I'm going to do the same thing with this term. I'm going to plug this value in for a sub n, and I'm going to plug 11 in for n, and I'm going to write that right below this guy. So it's going to be negative 3072 equals a sub 1 times r to the 10th this time. Because remember, I'm plugging 11 in for n, and 11 minus 1 is 10. Now, with these, instead of subtracting or dividing, remember, we're trying to cancel out a variable. And instead of subtracting or adding, we're going to divide these guys. If we divide the two equations, my a sub 1 is going to cancel out. It's going to be really nice. So I'm going to go ahead and use my calculator here. Negative 196,608 divided by 3072. Oh, that's a nice number. It's 64. And then over here, so the a sub 1's cancel. I'll cross those out. And then use your rules of exponents. When you're dividing with the same base, you subtract the exponents. And 16 minus 10 is 6. This is the reason why I like to put the bigger term number over the smaller term number. That way I had a bigger number on top. So when I subtract, I'm getting a positive number. Just makes it easier. And now you can do logs, but it's just easier to think about in this case. What number are you going to multiply by itself 6 times to get 64? And if you think about it, you should eventually figure out that 2 is the number. 2 times 2 times 2 times 2 times 2 times 2 is 64. So now we know what r is. And then to find the first term, you can take either one of these equations and substitute it back in. So I'm going to go ahead and take the bottom one just because the numbers are smaller. But I'm using a calculator, so it doesn't really matter. But I'm going to take negative 3072 equals a sub 1 times r to the 10th. And now we figured out that r is 2. And you can figure this out on the calculator. But you're going to get 1024. And when you do negative 3072 divided by 1024, you're going to get negative 3. And there we go. Now we know what r is, and we know what a sub 1 is. We're ready to plug into our formula. Whoop. And we get this. And that's as simple as we can get. So there you go. So even when they get a little more complicated, it's still not too bad. One thing I haven't pointed out yet, but I hope you've noticed, geometric series and sequences, they're exponential. Your formula for a sub n is exponential because the variable is in the exponent. And I just realized I didn't plug in my a sub 1. That's 3. Negative 3. There we go. Oh, I got it. But this is exponential right here. So remember, arithmetic had a linear formula for a sub n. Geometric have an exponential formula for a sub n. So you can always spot them very easily. Okay, so that was first example. We got 2 more. So the second example. Now let's look at sums. We have 3 more examples. Full disclosure. Let's say find the sum. And let's say that one of them is the summation as n goes from 1 to 8 of 5 times negative 3 halves to the n minus 1. All right. Well, remember we had a formula. First of all, you know this is not infinite because the upper limit is a number. So now you know that your formula is going to be s sub n. Actually, I'll put it over here. S sub n equals a sub 1 times 1 minus r to the nth over 1 minus r. Let's make sure we got everything. So remember a sub 1, that's your first term. Your first term, in this case, since n equals 1 is our lower limit, we're starting at 1. If we plug in a 1 here, 1 minus 1 is 0. Anything to the power of 0 is 1. And 5 times 1 is going to be 5. So we know our first term is 5. R is easy to spot. R is always your base. R equals the base. Because remember, R is the thing you're multiplying by each time, and the base is the thing you're multiplying by each time. So just look at your base. Your base is negative 3 halves. Yay! So now we're ready. We can just go ahead and plug in. Oh, how many terms are there? We need one more thing. We need what n is. Well, the number of terms from 1 to 8 is 8. So now we can plug in. The 8th partial sum is 5 times 1 minus negative 3 halves to the power of 8 all over 1 minus negative 3/2. And then we just plug that into the calculator. Now, one thing I want to point out is be careful, because we're so used to going, oh, minus negative. Yeah, just make a plus. And it's going to be tempting to say, let's make these both a plus on the numerator and make both of these a plus on the denominator. But be careful. You're fine doing that in the denominator, but in the numerator you have an exponent. And remember your order of operations. You have to do the exponent first. And a negative raised to an even power is positive. So this would actually turn out to be a positive number, and then you would be subtracting a positive. So just watch out for that trap. I see that happen a lot. But when you plug this into the calculator, and again, it's going to be fine if you use a calculator on this homework. But I'm getting, let me just see something. So I get this decimal answer of 49.257. However, this is equal to a fraction, which is negative 6,305 over 128. If you're using a TI graphing calculator, when you get that decimal answer on your screen, if you hit the math key and then there's an option number 1 says, it looks like this. Let's change to a fraction. If it can. It can't always, but if it can change the decimal to a fraction, it'll do it for you. So that's kind of a cool little thing to know. So there we go. There's our answer. Yay! Okay, so that was part A. Let's look at part B. So part B. Sorry, my cat down here meowing. He's funny. All right, let's look at the summation as n equals 4 to 10 of 3 times 2/3 to the power of n. So definitely pause the video, try this on your own, and then come back. Okay, hopefully you paused it and you're back. Let's check your answer now. So we know the formula is this. Let's make sure we know all the pieces. Now be careful because we're starting with 4. So it is going to be 3 times 2/3 to the power of 4. That is the 4th term. And when you work that out, you're actually going to get 16 over 27. So be careful with that. Okay, we need an R. R is always going to be your base, which is 2/3, and we need an N. And remember, N is the number of terms. So from 4 to 10, you actually have 7 terms. And again, think of it as if you were assigned problems 4 through 7 for homework, how many problems are you going to have to do? You're going to do 10 minus 4, which is 6, plus 1 more. You have to do that, problem number 4. So you're going to do 7 problems. But then you have everything. Now you can go ahead and plug it in. So we are looking for the 7th partial sum, which is 16/27 times 1 minus 2/3 to the power of n, which is 7 over 1 minus 2/3. Then you plug that into the calculator. Be careful about parentheses. Make sure you put each one of those fractions in parentheses. Very important, this one right here. So the 7 goes on the 2 and the 3. But my calculator is giving me 1.673 and some change. And it wasn't able to change it to a fraction, so I'm just going to leave my answer like that. There you go. There's that example. Second example down. 2 more to go. But the good news is the next 2 examples are much quicker. So we're on the downhill swing. Yay! Let's look at infinite sums. So let's look at this. Find the infinite sum. And definitely, I didn't say this for the first example, but I should have. as always, pause the videos, try these on your own. You have the formula. See if you can figure out how to do it on your own. I'll go ahead and put both of them here. The first example is going to be the summation as n goes from 3 to infinity of 1/4 times 2 to the n minus 1. And the second example is going to be the summation as n goes from 3 to infinity of 1/4 times 1/2 to the n minus 1. So give those a shot, pause the video, and then come back. Okay, so hopefully you paused the video, tried these on your own. Let's look at part A. So we do have a formula, and remember the formula, put it up above here, is a sub 1 over 1 minus r. It's a nice simple formula, but very important. The absolute value of r must be less than 1 in order to be able to use this formula. So always look for r first. In part A, r is 2. The absolute value of r is not, doesn't look like it, not less than, is not less than 1. So you can't use the formula, and the sum diverges. The sum doesn't exist. And you're done. Like literally, that's it. Yay! Okay, let's look at the second example then. The second example, r is the base, and our base is 1/2. So this time the absolute value of r is less than 1. We're good to go. We use the formula. I have it up here. So we need the first term, and this time the first term is plugging in a 3. So I'll actually put this off to the side here. A sub 1 is going to be 1/4 times 1/2, and it's going to be to the power of 3 minus 1, which is 2. And when you work that out, you're going to get 1/16. So there's our numerator. And the denominator is just 1 minus r, but we already know r is 1/2, so it's 1 minus 1/2. And please don't take your calculator out for this. I'll be so sad. When you do, remember when you divide fractions, multiply by the reciprocal, 1/16 times 2 over 1, the sum is 1/8. And there you go, there's your answer. I needed to do that, sorry. I can't box it otherwise, it was too low. So, not so bad. Infinite sums are pretty simple. You just have to remember to be on the lookout, is the absolute value of r less than 1? Because there's nothing to keep you from plugging in 2 into the formula. There's nothing to say, oh, let's just go ahead and plug this formula. Let's plug in a 2 for r and figure out what the first term and plug that in. But if you do that, you're going to get a number, but it's just gibberish. It doesn't mean anything. So be careful. Always look for r first. All right. The example is going to seem like it has nothing to do with what we've been talking about. So why the heck am I doing it here? This is the last one. And there's no part A, part B. It's just this. Express 0.416 repeated as a rational number. Remember, whenever you hear the word rational number, rational, that's the key. Think fraction. But mathematically speaking, when we say rational number, we're saying a fraction where the numerator and denominator are integers, positive or negative whole numbers. So basically, they want us to write this repeating decimal as a fraction. How in the world does this have to do with geometric series? Well, here's how. We can think of 0.416 bar as this. It's exactly what it means. You're just repeating 416, 416, whoops, over and over and over again. Or we can write it like this. It's 0.416 plus 0.000416 plus 0.000000416 plus 0.00000000416, and so on. That would be the same thing. But now let's look at how we can write this. So we have the first, I need bars on these. My bad, sorry about that. So we can have this, but then we've just taken this and multiplied it by something to get that. So 0.416 times, well, we moved the decimal over 3 places, but we've moved it 3 places to the left. That's multiplying by 1/1000th. Then for the third term, we took 0.416, but now we've gone 1, 2, 3, 4, 5, 6. We've gone 6 places to the left, or we could say 3 places to the left twice. 1/1000th squared. And I think you know where I'm going with this. The next one is going to be 1/1000th cubed, and so on and so on and so on. It's an infinite geometric series. Every single time, we're just multiplying by another 1/1000th. Infinite geometric series, where a sub 1 is 0.416 and r is 1/1000th. And the absolute value of r is less than 1, we can use our formula. So the sum is the first term over 1 minus 1/1000th. And now we just have to simplify this. This is not a rational number. Yes, it's a fraction, but the numerator is not an integer and the denominator is not an integer. So it's going to simplify very easily though, and they always do, which is nice. 1 minus 1/1000th, 1/1000th is 999 over 1000. But again, when you divide by a fraction, you are going to multiply by the reciprocal. And then look at this. We're going to take this decimal and multiply it by 1000. Remember, you put this over 1. You multiply it over, or multiply it by 1000, you're going to move the decimal place over 3 places. It's going to be 416 over 999. And then see if you can simplify your fraction. The nice thing is, just by nature of the denominator in these, you're always going to have like 9/10ths, 99/100ths, 999 thousandths. You're always going to have a bunch of 9s in the denominator. And remember the trick to see if something is divisible by 9 is look at the numerator and add up the digits. 4 plus 1 plus 6 is 11. 11 is not divisible by 9, therefore the numerator is not divisible by 9. That works for 9s and 3s. So the digits in the numerator add up to 11, which is also not divisible by 3, so this fraction's not going to simplify. There it is. And you can go ahead and try that on the calculator and see if you actually get 0.416, 416, 416, 416, and so on. And you're going to see that you do. So repeating decimals are just geometric series in disguise. And then that's it. So your only video. I know this was a long one this time, but at least it's only one video. And have fun this week. Bye.